Welcome to another episode of Learn Live. In today's session, we're going to be learning about how to train and evaluate classification models. My name is Ruth Yakubu, and I'm a cloud advocate at Microsoft. I work on the AI and machine learning team, and I am joined today with my colleague, David Smith. David is the developer advocate lead for AI and machine learning.
Thanks, Ruth. It's great to be here. I'm really excited about showing everybody how to do classification models. I remember learning about this back in my statistics classes way back when, and logistic regression and binomial models were all sorts of a mystery to me back then, but it's actually pretty simple. So I hope we get to explain it to everybody on the call here today.
Yeah, it's funny, of all the different models, classification is my favorite. So in today's session, for the audience, if you can go to the URL that's provided, that will lead you to the actual module that we're going to be covering. So you can follow in real time as we're presenting. And also, if you're using a mobile device, we have the QR code. Feel free to scan the QR code and it will do the same. It will take you to the module. And this is a fun session for us to learn. So be interactive, engaging, and yeah. One thing to add is MS Learn module on top of this module has a lot of useful courses that you can take. And one thing I like about MS Learn is a lot of the courses are interactive. So you can watch videos on MS Learn. The courses are self-paced. You can practice and upskill your skill and apply it to real life where it's important.
Yeah, and one really cool thing about this module, of course, is that it's interactive in that you'll get to run all the Python code, all the Scikit-Learn code that implements these classification models right there directly in the Learn module. You don't need to have an Azure account. You don't need to have access to the cloud. It's all going to do that for you. So this is a great way to learn how to use classification. And during this course, you'll learn how to train and evaluate classification modules within the Scikit-Learn framework. So this is a great one to get into.
Exactly. And we have a chat, so feel free to say hello and paste any questions that you have for us. And we'll be more than happy to answer your questions.
That's right. And our Dalian producer, Laurent, is also watching the Twitch stream and the YouTube stream. So if you have any questions there, feel free to drop them into the chat as well. And Laurent will pass them along to us here at Learn Live TV. All right. So Ruth, do you want to get us into the intro to the module? Oh, Ruth, looks like you're on mute right there. Well, while Ruth is figuring out how to get off of mute, just once again, we're going to learn how to use classification and use that to train and evaluate classification models in the Scikit-Learn framework. So with that, why don't I give a little bit of an introduction into what classification actually is? And here is a little example that's going to help us motivate that. Let's imagine that we have collected data on a number of patients in a clinical setting. We've measured a bunch of data about those patients, perhaps including their blood glucose level, measured using, say, a finger stick device. And also for each of those patients, we have a diagnosis from a doctor about whether or not they are diabetic. So in this data record, you can see we've got data for about 15 patients or so. The first patient, we measured their blood glucose level to be 82, and the doctor diagnosed them to be not diabetic. So that's a 0 there, representing a negative case. On the other hand, if you have a look at the third row there, we can see a patient whose blood glucose measurement was measured at 112, and they are diagnosed as being a diabetic. So the big question is, can we use this information that we have, this ground truth about a bunch of patients, information we have about them and their diagnoses, to build a model which relates the information we have with the labels that we have? In this particular case, it might end up being some kind of a rule about if the blood glucose level is within this range or above this threshold, then we make a positive diagnosis, and otherwise we make a negative diagnosis. So this is a very simple example of classification. So classification is just a form of machine learning in which you train a machine learning model to predict which category an item belongs to. So the example we just gave, we have measurements perhaps not just on blood glucose, but perhaps also heart rate, weight, dimensions of certain body parts. We'll see in the data we'll look at in a minute. We've got a measurement of the tricep muscle as an indicator to try and predict a category, which one of two categories each patient belongs to, diabetic or not diabetic. Another example might come from, say, the marketing domain. We have a limited marketing budget, and we want to identify from all the potential prospects that we say might send a mailer to, which ones are most likely to respond to our offer. So the categorical responses there are respond or not respond. Now, in both of those cases, there are two categories. So that's kind of a binomial or binary classification. But we can go beyond that as well. We can do multi-class classifications. Going back to the diagnostic setting, we might not simply be trying to predict whether somebody is diabetic or not diabetic, but trying to predict whether they have no diabetes or diabetes type 1 or diabetes type 2 and so forth. So that's three different classifications we might take a look at. You might have heard of the famous penguins data set, where they measured the body extremities like wing length and bill length of three different species of penguins in Antarctica, Adelie penguins, Gentoo penguins, and emperor penguins. And then we might try and predict from those body measurements which of the three types of penguins they represent. And so it's a three-way classification. But all of these are classification problems, which is a machine learning problem. In this particular example, we're going to start with binary classification, as I mentioned. So that's classification into just two different categories. Now, what's actually happening behind the scenes, and this is an important thing to remember, that anytime we're thinking about categories and predicting categories, what we're actually doing is trying to estimate probabilities that somebody is going to fall into that case. Now, the reasons why it's probabilities and not just yes or no is because of natural variation. Think of a person who has a blood glucose level at 90. That might indicate that they just have a naturally high blood glucose level, or it might indicate that they are actually diabetic. And you might imagine there might be 100 different people who all have a blood glucose level of 90, but they wouldn't all be positive or all be negative. So in that case, what happens is we assign a probability to that case, and then we try and build a model to estimate that probability from all the data we have, which we then use that trained model to do the classification. I see Ruth's back. Welcome back, Ruth.
Yeah, that's the beauty of doing a live show.
Yeah, a fire alarm happens at the worst time.
Yeah, that's when all the equipment's shut down.
All right, well, Ruth's back. But anyway, just to finish up the discussion here. So we're doing classification. And this is just one example of a supervised machine learning technique. And it's supervised because we have known feature values, known labels. We know ahead of time for all the patients in the data that we're analyzing, whether they are diabetic or non-diabetic. So these are the labels that we have that are assigned by an expert, in this case, a doctor. And then associated with each of those patients and their labels, we have data or measurements or features associated with each of those patients. So this is a very common scenario. It typifies supervised machine learning, and this binary classification model that we're building is just one example of it.
And David, I have a quick question.
Yeah.
So when we say supervised, what does that mean? Does that mean the developer is right there looking at the training when it's happening?
Now, supervised in this case means that we have labels associated with the data. In this case, the diagnosis of diabetes that we're using to drive the underlying model. Now, the contrast to that might be an unsupervised technique, where we just took all the data from the patients, their blood measurements, their weights, their ages, and so forth, and didn't have any information about diagnoses. But we tried to perhaps cluster them together into like groups and maybe do analyses from those. That will be an unsupervised technique. But because we have the actual diagnoses that we're trying to predict, this makes it a supervised machine learning technique.
That makes sense.
All right. So Ruth, I'm actually going to go back to our data right here. Okay. So here's some data we have on patients with blood glucose levels, and we have some diagnoses from the doctors. Can you see from that data a way, if you knew a blood glucose level, to make a prediction about whether or not somebody was diabetic?
Not really. I'll need some backup information, because those metrics can easily be another data set. It could be people's weights.
That's right. It's definitely not obvious there. Even when we've only got one feature here, blood glucose. One of the things we could do is sort it. So let's have a look at a chart of all the blood glucose levels. And here's just 8 of them on the x-axis. And on the y-axis, we'll put our diagnosis. Now, a diagnosis is binary. It's just 0 or 1 in this case. So it's a chart that is not very interesting. Everything is right there on the edge. But one thing that we can see immediately is that for those patients with the lower blood glucose levels, they tend to be the zeros, not diabetic. And for those patients with the higher blood glucose levels, they tend to be the ones, the diabetes diagnosed patients. So that looks like blood glucose is giving us some information about the diagnosis here. And that's a basis upon which to build a model. So that's going to actually go to what the machine learning is going to do, is going to build that model for us. And remember, I talked about it all being probabilities. So what we're actually going to get out at the end of the day is a model like this red line, which associates with us, for a blood glucose level on the horizontal x-axis. It's going to tell us what the probability of somebody who has that blood glucose level has of being diagnosed with diabetes.
So the whole plotting, like taking a blood glucose and plotting on the axes and finding out what that curve is, that the whole process of what training is?
That's exactly what training is. That's exactly right. So that's the machine learning process, the logistic regression, is essentially going to do a best fit curve of this S-shaped curve, which is called a logistic curve, which is a great way of representing probabilities, because it starts off at 0, increases smoothly. I'm trying to get in camera here, increases smoothly to 1, and then levels off at 1. So it's a standard type of curve. Another great thing about the logistic curve is it extends not just to one variable like we have here with just blood glucose, but we can include data about multiple variables or multiple features to make our prediction and probability. And what you can see here is a kind of, this particular curve aligns pretty well with what we're thinking, because for anybody with a blood glucose level less than 102 or so, it's basically saying you've got no chance of being diabetic. For anybody with a blood glucose level more than about 107, it's saying you're pretty certain to be diabetic. And then between those two ranges, from 102 to 107, there's an increasing probability of being diabetic. Now, this is a real toy example. We've only got one variable. There's no variation here, but it's just to illustrate this whole idea of the logistic curve relating to probabilities, not these ones or zeros.
And who makes the decision that maybe if somebody has a blood glucose of 102 versus 106, that you do have, you're diabetic?
That's a really good question. Let's take the example of 105. All right. So if somebody walks in and they have a blood glucose level of 105, then we can follow the line across, and we see that represents a probability of just over 50%. Now, what would you do about that? What if a diagnosis of diabetes meant that you had to go to the Quest lab and get 3 more blood tests? Do you think that's a good thing or a bad thing?
I think that's a good thing, because for me, I'll need a little more certainty. If it's above the threshold,
Yeah.
It's a 70%, but for me, I'm not confident yet.
Yeah, that's right. I think that's right. You know, I think if my doctor thought there was a 50-50 chance that I might have diabetes, I'd want my doctor to send me for some more blood tests to confirm that yes or no. But what if it meant that if you thought I had a 50% chance of diabetes, that I needed to go to hospital and have a major surgery? Does that seem like the right thing to do?
So it delays things. Yeah.
Yeah. And that's kind of the point here is like our model is only telling us the probability of something happening. But the decision about what to do is really up to the experts here. So in this particular case, in our particular toy model, let's say we set our threshold here to be 50%. If the probability predicted is more than 50%, there's some kind of intervention. If the probability is less than 50%, there's no intervention. And so what that means in terms of a rule is if we trace back down from the 50% line to the blood glucose level, our rule, which is coming from this decision about the threshold, is that for anybody with a blood glucose level more than 104.8, then we treat them. And if it's less than 104.8, then we assume they don't have diabetes and we let things go. So, but where that threshold is set is a clinical decision that'll be made by doctors and experts or whoever is responsible for the particular study that's being done. But it makes a big difference in terms of what our predictions are ultimately going to be on the binary scale.
That makes sense.
All right. So there's just an arrow that's pointing directly to the axis there. All right. So Ruth, why don't you take us into the Learn module and show us how to import some data about diabetes and create a model just like that and make some predictions.
Okay. So before I get to the exercise, one thing I wanted to share with the audience is once you land on the Learn page, the main page, what you're going to see is basically what we covered, what you're going to be learning, what the objectives are. And one of the good things I like is it gives kind of a prerequisites. So what's needed for this particular module, you need to have like some basic mathematical concepts, knowledge of mathematical concepts. And also, since the code is going to be in Python, it also alerts the user that it'll be helpful for you to understand Python. And another thing about the MS Learn modules are, if you look under this particular module is part of a bigger learning path. One of them is creating machine learning models, and that will cover a whole different types of models you can create for machine learning, let's say regression models. Then there's another course for the foundation of data science for machine learning. And this one is actually good because I believe after you finish taking the different bite-sized modules in there, you can actually get certification.
That's right. There's a data science engineer certification within Microsoft Learn, and these learning paths that you see right there will give you a good foundation for getting a start on the exam for that. So there's lots of great stuff in there. Yeah. Hey, Ruth, one thing I did notice, what's the deal with that 1000 XP that's right up there at the top of your screen? A bit further.
On top of the screen?
Yeah, Sirius has 1000 XP up there in the corner. What's that all about?
Oh, you mean this?
Yeah, yeah.
Okay. So that means after taking this course, those are actually the points that you're going to earn. So if you notice, I haven't logged in, but if I logged in, it'll show what level I'm at. So it'll show, let's say I'm at level 6. It'll show how many points I need to earn in order to be like maybe a level 10 or whatnot. So,
all right. So if you're logged in, then Learn will keep track of all the courses you've taken, the modules you completed, everything like that.
Exactly.
Cool.
So I'm glad you asked that. I should have logged in, but that's the beauty of rebooting your laptop when you're presenting live. Yeah, but if I was logged in, it's actually a green bar that shows the current level that you are. And each time that you complete a module, you can see those numbers increasing. So let's go through the modules and get to the actual exercise.
So if everybody
And-
following along at home, we're up to unit 2 of the module right now.
Okay.
Yep.
So you've already covered what's classification.
Yep. Unit 2 is just some background, which we've covered just a minute ago.
Okay. Perfect. So the next thing I'm going to do is the good thing about the different Learn modules that Microsoft has is it comes with a sandbox. So just in case you don't have an Azure account, that doesn't hinder you from completing any of these courses. The programming modules come with a sandbox. And with that, for this, we can just activate our sandbox. So as you can see, it didn't take that long. Once you activate, all you need as a end user when you first come to take the course, you just need a MSDN email account, and you'll be able to log into the sandbox. It doesn't take that long, as you guys saw in real time.
So Ruth, then, like if people are doing this exercise at home but don't have Python, say, installed on their laptop, can they do these examples that you have in front of you here?
Oh, yeah. Actually, that is a good thing that you mentioned. I forgot to mention that. So this sandbox is actually a sandbox that behind the scenes is a data science VM that this sandbox is built on. So it already comes with Python installed. It comes with Jupyter Notebook. It comes with let's say all the we're using Scikit-Learn in our the framework that we're using in Scikit-Learn. So we don't need to go and import all of that. It has all those libraries. So
all I need on my desktop then is just a browser. All the computations are happening in this sandbox in the Azure cloud, and all the software I need is all ready to go for me already.
Exactly.
Right.
So the very first thing I'm going to do is, since the use case is on predicting whether or not a patient has diabetes, the very first cell.
Now hold on, Sal, like this, you're in Microsoft Learn right here, but this looks like a Jupyter Notebook. What's that all about?
Yeah. So kind of like how I mentioned, this is a Jupyter Notebook sandbox. So there are different sandboxes actually that Microsoft has. Since this one is a data science one, it's actually a Jupyter Notebook sandbox. So for the audience that is used to using Jupyter, all the different controls that you're used to using for Jupyter Notebook, you have there. So for running this module, you can either click on Run All, or you can go cell by cell. And also, if you have meta cells, if you want to put comments in there, it has all of that. If you have, I said meta, markup, markdown cells for commenting, it has that. And cells for coding, it has that. So for the very first cell to run this notebook, basically we're using pandas. And this URL is where the diabetes data is located. So the good thing is it has the ability to grab data externally, and we're going to be using the reads CSV object.
It looks like you're downloading data from GitHub into the sandbox and then using pandas to read that into Python.
Exactly. So I'm going to run that. And that's one thing that I like because once you start taking these, the different courses, sometimes you don't know the size, or I may download the data locally but forget to remove it. And depending on what the size of the data is, it's going to be eating up my memory. So that's one thing I like, that everything is downloaded into the sandbox, and The notebook knows exactly where to store things.
And this is a pretty decent data set, if I remember rightly, about 15,000 records.
Yeah. And the very good thing about it is you can also, after running that, we can take a look at the data before we actually start training the model. So kind of like the introduction that you gave us, we have patient data. So we have information like the number of pregnancies a patient may have, plasma glucose, diastolic blood pressure, tricep thickness.
Around here, I think. Yeah.
Oh, yeah. So all those some of the medical terms I'm not too familiar with. BMI, age, all of those are the different data. And I'm assuming, based upon your introduction, these are the data that maybe a subject matter expert, like a clinician or doctor, has identified that, okay, if you want to classify somebody as diabetic or not, these would be some of the data that you need.
It could be useful, yeah. And unlike the example I gave earlier on, which just had the one feature, which was the blood glucose level, now we have 7 features to work with for all of our patients.
Yeah. So another thing is, you mentioned that you talked about supervised learning.
Yeah.
So for me, when I'm looking at data, and okay, it's a classification and whatnot, these are some of the telltale signs, because this is patient data. It was collected, but we also have this column called diabetic.
Yep.
So it's actually showing the outcome, the true outcome, that, okay, given these different measurements that the patient had, they actually had they were diabetic or not.
That's right. And for our particular example here, we're going to assume that's our ground truth. Like some doctor has made that diagnosis about whether somebody is diabetic or not. But now we're going to try and learn from that experience of these 15,000 patients, looking for patterns amongst those 7 features that will help us predict for a new patient that comes in, given those 7 features rather, are they likely or not likely to be diabetic based on this experience of all the other population?
Yep, that's correct. So one of the things in building a model, especially supervised, is you have to identify what the features are. So similar to what we're talking about, the features would be what the doctor or the subject matter expert in whatever use case that you're dealing with has identified that, yeah, these would be the areas that you need to look at, the patterns you need to look at in order to predict whether or not somebody is diabetic. So in our case, we put all the features into one array. And it's very important, since this is a supervised learning. We also have to specify what the label is. So the label would be the column that said diabetic. And that's how, during the training process, the algorithm is going to know, okay, where is the data patterns that I need to be looking at, the characteristics, and what would be the output as they're training.
Why don't we run that cell and have a look at some of the data? And you might want to run the next cell as well, Ruth, because I know that one's going to take a little time while we're chatting about this one.
Yes, that is correct.
Yeah. So what we can see here is just the first 4 rows of data, and we identify the 7 features. So the 7 data records that we have, the blood pressure and so forth, and then the label associated with each of those 4 records. So the first one is label 0, not diabetic, not diabetic, not diabetic, and then the 4th patient is labeled as diabetic. And we're going to try and use the information in our features to try and make those predictions. And what that next cell is doing right now is we're going to have a look at some of the distributions of the data of those 7 features within each of the 2 groups for the 2 groups, the diabetic and the non-diabetic. I know because this is running in a new sandbox. This one takes a little while to get to load in some fonts from MATLAB, Matplotlib rather. But what go ahead, Ruth. Yeah.
Yeah, I think for me, this is actually good before in real life, realistically, before we start training a model. Sometimes we don't quite have all the features defined. So this is a good way of exploring how your data is how your data looks like before you go into training. So I like that.
But as a data scientist, it's one thing to look at tables and look at numbers, but I really want to see data graphically before I, can make some judgments about whether the data is useful or meaningful or even correct. So what we've done in this next cell here is we created box plots of each of the 7 features, divided up into the 2 groups of the diabetic patients on the left, the non-diabetic patients on the left, the zeros, and the diabetic patients on the right. So let's look at this one right here you've got in front of us here, Ruth, the plasma glucose one. All right. So first of all, for anybody who's not familiar with a box plot, it's kind of like a simplified version of a histogram, but on its side. So the green line that you see there on the left-hand side box plot, that is the median of the plasma glucose measurements for the non-diabetic group. So the median there is about, 96 or so. Now compare that to the median for the diabetic group, which looks to be at about 108. So there's a higher median plasma glucose for diabetic patients than for non-diabetic patients. But is that a significant difference? And the way you can judge that is by having a look at the spread of the data. And that's what the box plot does. The actual box in the middle is the interquartile range. So there's 25% of non-diabetic patients have a blood glucose less than 80. And 25% have a blood glucose more than about 126. Whereas for the diabetic group, those numbers are about 99 and 132. So there's a higher range for the diabetic group. Again, more evidence that it's useful. Another thing we see is the outliers, and those are the circles that we can see in the diabetic group. There's a lot more extreme values, both on the high side and the low side for the diabetic group when it comes to plasma glucose. And then we can look through all the other variables as well and get a sense of, whether they give us information about about diabetes rather.
Yeah, one thing that also worries me is when looking at the data, some of these ranges actually overlap as well.
Exactly. And if you have a look through the other variables, you'll see there's overlap in just about every case. You have to sort of scroll through the actual cell there. And that's pretty typical. That's the whole reason why we use machine learning, is because a lot of the time these relationships aren't just obvious to the eye. But machine learning techniques like linear logistic regression can filter out a lot of the noise to get the signal here, which there is a relationship when we combine all these 7 variables that's going to help us to predict diabetes or not, as we'll see.
Yeah. Seem like the age has a lot of outliers.
That's a really interesting one. So what that is telling us is that almost all of the non-diabetic patients are less than 32. There are some outliers, a few of them, but not many compared to the overall distribution. Whereas for the diabetic patients, there's a much broader distribution of age. So age is going to be a useful variable for us to make predictions too.
Yeah. Okay, so now that we've analyzed the data, here it may look trivial, but David, you and I know in real life that data analysis portion is very time consuming, especially when you're mentioning looking at just static data or having all these different tools, different ways of visualizing the data.
And actually, in this case, we've got nice, clean data ready to analyze. In my experience, just the process of even getting to this point can take a long time. But we're focusing on the training, not the data analysis here.
Yeah. So to move on to the next cell is actually splitting the data. So now that you have kind of like how David said, you don't just get data and say, yes, it's good to be trained. There's a cleansing process. So let's say you have your data ready, everything is cleansed and ready to be trained, the next thing is Scikit-Learn has a class already there. It's called the train test split. And in computer science, it's very important when you're training your model to split your data. So in the diabetes case, we're splitting it 30% of the data we're going to allocate to be our test data. And 70% of the data should be allocated for during the training process because we need more data to do the training.
That's right. And the reason why we do that, Ruth, is because like we're essentially going to be giving our model an exam in a minute. We're going to test it to see like how accurate is our model doing when it actually tries to predict diabetes. Now, the problem is to do the testing, we've only got the data we've got. And if we include all the data in the model, then essentially we're sort of having an exam on this model with data it's already seen. So we're going to hold back 30% of the data so the model will never see it when it's doing the training. And then later on, we're going to test it. So for that 30% you've never seen before, giving you a prediction for the first patient, the second patient, all 4,500 patients, and then we'll count the number of times the model got that right. And then we'll look at that accuracy to decide whether or not the model is doing well.
So are you insinuating that machine learning can also memorize?
Machine learning absolutely can memorize. That's actually a big problem with overspecification of models in that they don't generalize. Now, I can train a machine learning model to get the answers exactly right for all 15,000 patients in our data set, just with a rule that says, if weight is 72 and blood glucose is 98, then predict diabetic, because that's what we saw. That's not going to be any use to us in the future when a brand new patient comes in that the model has never seen before. So that's why we hold back this test set to verify that our model hasn't been overspecified and does generalize to data it hasn't seen before.
Yeah. Okay. Yeah, thank you for actually pointing that out. I always think of, let me split the data and move on. But yeah, I'm glad you pointed that out as well. One thing to specify is when we're splitting our data, if you guys notice, we have X and Y. So there's a X train and an X test. Then there's a Y train and a Y test. This just basically means that, the difference between the X and the Y is all of the X are going to be your features, the attributes that SME identified that these are the telltale signs of predicting whether somebody is diabetic or not. The Y is only going to have one value. It's going to be the actual label of yes, 1 or 0 or yes or no, somebody has diabetes. So when we're training, during the training process, we use the X train and the Y train when we're training the data. And kind of like how David mentioned, when we're verifying whether our model did train correctly, we
use those test sets.
X test. Yeah. Wow. So it looks like the data set had 15,000 records in there. So yeah, it seemed like we're allocating 10,500.
So now we've got our 10,500 training set. We can go ahead and train that model.
Yeah. So let's move on to training. So the next thing about the logistic regression, the Scikit-Learn framework is it has a algorithm called logistic regression, and it does the classification. So in order to train the model, we basically just call the logistic regression. And since we're dealing with a small data set, one of the hyperparameters that we specify, this field here, by default is linear, but if you have small data sets.
Yeah, there are lots of different algorithms out there for fitting logistic regression. If there are any statisticians watching now, you might be familiar with iteratively reweighted least squares. This is not that algorithm. It is that linear algorithm. So we have to specify some parameters like this regularization rate right here.
Yeah. And as you can see, for the training, we're all specifying the X train and the Y train. So I keep forgetting to run the model, the cell. So basically, what we've done is we've gone ahead and trained the model with
And so now we have a new Scikit-Learn object, right, called model, which we're going to interrogate now to get some information about the model that it created.
Yeah. So let's see how well the model did. So we have the model. So now we're doing the testing. So we pass the features, the different patient characteristics or the different measurements we got from the patient.
From the test then, yeah.
Yeah, the different tests that we derive from the patient. And the model, when we call predict on the model makes a prediction. Okay. So we're printing the prediction, and also this is a prediction of the model, and this is the actual value of the model. So
all right, so let's see how it did. So our model then for the first test case predicted 0, not diabetic, and that corresponds to the true data, not diabetic. In the second case, predicted not diabetic. That was the actual data, not diabetic. But in the third case, our model predicted not diabetic, but the actual patient was diabetic. So I made a mistake in that particular case. So what we should probably do now is have a look over all of our test cases and see how it did.
Yeah. So another common thing we hear is how accurate is your model? So Scikit-Learn actually has a function called accuracy score, and you can call that on both your test data and your prediction, and it will give you the score, the report card of your model that you just trained. So I don't know, David, it looks like we have 0.789, so like I'll say 79% accuracy. Yeah. Is that good?
So in our data, yeah. So let's so in our test data set, our model got an accuracy of about 79%. Now, also remember that this is based on a threshold of 50%. So this is basically any probability predicted bigger than 50% got assigned to be diabetic. Anything below 50% got assigned to be not diabetic. And we could actually change that accuracy score by setting that threshold differently. And, where we set that is, again, going to have a clinical aspect to it as well. We could be 100% accurate for all of the patients that are diabetic simply by diagnosing everybody as diabetic. But that's not going to be, so 100% accuracy for that subset isn't going to be very useful to us. Whether this model is accurate at 80% is really a question of comparisons between all the different models we might try, different sets of data we might try. And there's always going to be a limit because there's variation in all natural data. But we judge that accuracy by the different types of models we might try against it. And in fact, why don't we actually switch gears here and talk a little bit more about evaluating classification models from our slides, and then we'll return from module 5.
Okay, that's a good idea.
Okay, so let's just recap quickly what we did just then. We created a model that would predict from our test data from a number of features, and here just one. It would try and predict this third column, the Y hat, diabetic or not diabetic. And then we compared that to the actual data, which we know because this is supervised learning. We have true labels for this test data, and we can make the comparison. This one was correct. This one was correct. This third one was wrong. This fourth one was wrong. This fifth one was correct. This sixth one was correct. So for this 6 data points, this model was 50% correct. But as I was just alluding to, overall accuracy isn't the whole story because there's different types of errors. Okay. What we were looking at then was true positives and true negatives compared to predicted positives and actual positives and actual negatives. And we can sort of summarize all that in something called a confusion matrix. So let's say that the actual known labels were 0 not diabetic. We might either predict that they are not diabetic, so that's a true negative. We might also predict that they are positive, and that would be a false positive because we know in that case it was negative. Similarly, down here in this bottom right left-hand corner, for the patients that we knew were diabetic, if our model predicted they were diabetic, that is a true positive. Whereas if it predicted they were negative, that is a false negative, or false positive rather. So, we can just label the 4 cells of what we call this confusion matrix with the true negatives, the true positives, the false positives, and I've got a typo on the slide. It should be false negatives, of course, down there on the left-hand side. Now, whether we care about false positives or false negatives or true positive or true negatives really, again, depends on the clinical situation. You had a question there, Ruth?
No, I think it's kind of good because we always hear about the accuracy, but it's kind of good when we have like a score to go and figure out, okay, if you said it was 79% accurate, then what happened to the 21? What's going on with the 21%? So I'm glad that we have things like the confusion matrix to kind of show us how the model is behaving, the performance of it, and where things are allocated.
Yeah. So if our goal is to detect as many instances of a disease as we can, we might want to minimize the false negatives.
Yeah.
We want to set our threshold really, really low. So if there's any indication at all that somebody might have a disease, we will do the follow-up, we'll do the further investigation, or we'll assign them a drug or whatever the situation may be. So we might want to minimize false negatives. On the other hand, if it's a marketing campaign, when all we're trying to do is perhaps identify the top 1,000 customers to send an expensive mailer to, we don't care too much about false positives in that case. If we send it to the wrong people, big deal, it's a marketing campaign. All we're trying to do is optimize the ones that actually receive it. So accuracy is what I'm trying to say here, is that accuracy is not the be all and end all when it comes to these classification models. You might want to be considering false positives, false negatives, or a combination of all 3. And in fact, there are different types of metrics that let us do that. What were you going to say there, Ruth?
I was saying, I looked, when I was looking at the false positive, I'm just thinking of a situation where it said, it diagnosed you with a disorder, but let's say in a clinical sense, that's the operation table. Somebody is going to go and do like a procedure operation on me when it was a false prediction.
That's great. So that's a great example where you wouldn't want to have too many false negatives, because you wouldn't want to be putting somebody through a dangerous surgery unless you're really certain that it warrants the intervention.
Yeah, exactly.
All right. So I bring up all this because there are other types of performance metrics that people might want to consider other than accuracy. We looked at accuracy already. So thinking about our confusion matrix, that's the total number of things we got right, the true positives and the true negatives, divided by the total population size, which is the sum of everything in the matrix: true positive, true negative, false positive, false negative. But you also might want to call something like recall. So of all the cases in our data that were positive, how many did our model actually pick up and correctly identify as being positive? And that's the recall statistic, which is the number of true positives divided by the number of true positives and false negatives. On the other hand, we might prefer to look at precision. So of all the things that our model predicted to be positives, how many did it actually get right? And in that case, we're looking at the number of true positives divided by the number of true positives plus false positives. So these are all statistics that, depending on the situation, you might want to take a look at. And Ruth, I think if we go ahead to module 5, we can take a look at how to calculate those.
Yep. So what I'm going to do, since you already covered everything, and you already covered how to evaluate, I'm going to skip over and move on to module 5. So we still have time on our sandbox, since we had 2 hours. I just noticed that, so that's good to know. So the next thing is we've already, this is basically what we've done. So we're gonna see how we can optimize our model in this section. So this very first cell that I'm running is actually what we just
Now, that's still the same code we
completed.
ran before, just in one single cell, I think. Yeah.
Yeah. So kind of like in Jupyter Notebook, like when you move from one module to another, if I can't just go and run the cell needs to be completed before we move on to the other cell. But while we're waiting for the first cell to do the accuracy prediction or calculation, one thing I wanted to point out is Scikit-Learn actually also has another function called classification report. So all this information that David has shared with us, it's not something that when we're doing the training, we take out a calculator, especially when he was doing the recall. I'm like, okay, hold that thought. Out of all these numbers, let me figure out what the recall is. The good thing is Scikit-Learn actually has a function there that we can call, and basically we give it what the test data is and also the prediction, and from there it'll come up with the confusion matrix. Actually,
So I
give
can see
me a
you got put in a queue for that one. I've got it up on my screen if you want, Ruth. We can talk to that one.
yeah, if you can do that, that'll be helpful.
Yep.
Yeah, it looks like my
Oh
screen.
yeah, I'm in the same spot. Yeah, oh, this is my screen. Yeah, I'm just waiting for matplotlib to do its charts. But we're doing the same thing. We're importing the data from GitHub, reading it into Python using read CSV, defining our features and labels from the data, using the logistic regression model to actually fit the model with the regularization rate of 0.01. And then once it's finished loading in from matplotlib, we'll be able to print the predicted labels from the model and compare those to the actual labels, and then do that overall accuracy statistic that we did in just a moment ago.
Mm-hmm.
We'll have that finished.
And the interesting thing is a lot of people have the assumption that once you have your data, you do run your training and it comes out with the score and you're done. It's like, okay, yeah, I went out for lunch, had the training, and we're good to go. But what you just covered in the different analysis shows the complexity of training a model, because you can train it. Okay, a 79% accurate. Is that good or bad? Can we improve it? So these are part of the process that somebody running a machine learning or data scientist training models, they'll have to go through. And sometimes it may take a day, it may take a week, it can take weeks, months before you get that optimum model. So yeah, it is a fun process.
Okay. So I think we're going over here. We've run the logistic regression model in Scikit-Learn. This is the same information we saw before. It's the same data. We've got our predictions from the test sets. We've got our actual labels from the test set, and our overall accuracy from this model. Remember, this number is 78.9%.
Mm-hmm.
Okay. So let's do this next one. We're going to do this classification report. So tell us about that, Ruth.
So the classification, is that your screen or mine?
I think if we can return back to my screen, thanks, Lauren.
Yeah.
There we go. Great.
Yeah, because I was shutting down my kernel on the other end. So we don't want to go to that.
Yeah.
So yeah, don't be alarmed with the red bar. I was just shutting things down while David was talking. But basically, when we run this classification report, the numbers that we're seeing here is okay. The prediction, it predicted that 81% of the time, it predicted that the patient did not have diabetes when they actually um, did have diabetes. Then also here is the recall. So it's basically out of the cases where somebody did not have diabetes, how well did the model do in predicting that they did not actually have the diabetes? So
That's right. So those
80,
precision and recall statistics we can calculate then on each of the subgroups. So we've done it both for the patients that do not have diabetes and the patients that do have diabetes.
exactly.
Yeah. So we might, yeah. And there's also this F1 score here, which I'm not so familiar with. I've never used that myself in practice, but as I understand it, it's a combination of both precision and recall.
And it's just bringing balance between the precision and the recall.
Yeah.
And
actually, I got a question here that Lawrence put in from YouTube. Kevin asked us, what other metrics can we use for classification, and are metrics such as G-means commonly used? I'm not familiar with G-means myself, Kevin, but I think the lesson to take from all of this is that the metric that you should use to evaluate a model is really determined by the subject matter experts. So in this particular case, we'd need to actually go back to the clinicians, the doctors, the people that are actually consuming our model in practice, and ask them what's most important to them. Is overall accuracy for all patients the most important for you? Or is it more important to be accurate for patients with diabetes than without diabetes? Because that's going to influence a lot of things in terms of the features that we choose to include in the model, the threshold that we choose to do the classification, in this particular case of classification models, and all sorts of decisions about how the the predictions are presented in a user interface, for example. So I think I can't really answer your questions. Is a metric like G-means commonly used, without saying in all situations where you're wondering what kind of metric should be used, that is an opportunity to actually go and talk to the consumer of your model, the subject matter expert, and ask them what's important.
Yeah, I do agree because especially for industries where it's highly regulated, like healthcare, I'll say the more metrics that you can provide to justify the outcome of your model, the better. So,
right.
yeah.
And we're getting a little bit off topic here, but Ruth, of course, you're an expert in responsible AI, but we've got to remember, machine learning is a subset of AI, and the models that we build have consequences when they're deployed into practice, and they affect the lives of actual people. So Kevin, these are really important questions to ask about, what metrics should we use to decide whether a model is good or bad? And again, go to your subject matter experts, go to your consumers to ask that question about what is important for the people that are actually affected by the model. All right. So we had a look, Ruth, at the classification report for this particular model. It's given us the precision, the recall, the F1 score, and the support, which is just the numbers. So we can see here that in our test set, there are 4,500 total, of which 2986 did not have diabetes and 1514 did have diabetes. All pretty straightforward.
David, before you proceed, if you go up, in that box where it's comparing the diabetic, like where it says 1 for the people that have diabetes,
over here,
72 and 60 and 66, that's going more towards a threshold of 0.5. So that is kind of alarming if you're actually analyzing the data.
Something strange has happened to my screen. Sorry about that. There we go. What this is telling us is that the model's performance is different in the two different subgroups of diabetic and non-diabetic. So on both precision and recall, our model is more accurate for non-diabetic patients than it is for diabetic patients. And again, that's an important thing to know depending on how clinically that data would be used.
Yeah.
All right.
And you have covered the true positives and the true negatives.
Yep.
And all of this, like one thing I also want to point out is similar to like accuracy score, getting the confusion matrix, getting the precision score or the recall. Scikit-Learn does a good job providing those functions for us, so we can provide our predictions that we got from the model and also the actual values from the Y test, and be able to look at those numbers and have those conversations to evaluate whether, okay, do we need to, is the model performing well, or do we need to go back and re-optimize or tune our model?
That's right.
So
So what we have here is we just did a little cell of code here, which calculated the overall precision and the overall recall across both of our subgroups, the diabetic patients and the non-diabetic patients. So this is another statistic we might want to use to evaluate the performance of our model if we feel that both subgroups are equally valid in that sense.
Mm-hmm.
All right.
The good thing is, I think my kernel, after I rebooted it, I accidentally shut it down. That's why we saw that red line. But
Right.
yeah.
Do you want to continue here, or do you want to take over from there?
Yeah, actually, we can continue here. Then I can take it up. Yeah.
So we've got the confusion matrix here. So we talked about that a minute ago, calculating the true positives, the true negatives, the false positives, and the false negatives. And this is what we have for our test set: 2637 true negatives, 914 true positives, 349 true negatives, so false positives rather, and 600 false negatives.
Mm-hmm.
All right. What's happening in the next section here? We're going to have calculate the predicted probabilities from each of our models. So remember, we said earlier on that the underlying model isn't just predicting zeros and ones, it's actually predicting probabilities. And we can find out what those are with this predict_proba function from Scikit-Learn. And for our first value in the model, you might remember our model predicted 0, so not diabetic. And that's because the probability of a 0 was 0.81. And then the opposite of that, 1 minus, is 18%. And we can actually have a look at the probabilities for each individual prediction separately. And that's going to be really useful if we want to set a different kind of a threshold when we actually make the clinical diagnosis of yes or no. Okay.
Okay. So now we can, another way, as we're talking about improving the process of improving your model, or seeing whether, okay, I just ran a model. There are different ways, similar to what the user mentioned with the Q matrix. There are also different matrix we can look at. So one of the things that is out there is the ROC curve. So for some of these, for the actual model performance, you can also graph some of these behaviors and also see on a graph how well your model is doing. So as you can see on the y-axis, we have the true positives, and on the x-axis, we have the false positives. And the line, diagonal line, is actually where they intersect. So just say like, okay. So what we're trying to analyze is how well are we getting to the true positives as we're plotting each and every patient's prediction. How well are we getting to, because we want to get to the true positives, right? So,
and that actually relates, Ruth, to a question that came in from Ravi in the chat, who asked, how do we determine which metric to use? So this is a really good example, in fact. We determine which metric to use by talking to our consumers of our models. And if the doctor said to us, like, the most important thing is that we optimize for true positives. We want to make sure that if somebody is actually diabetic, then we diagnose them as diabetic, even if that means diagnosing a lot of people that are not diabetic mistakenly as diabetic. So let's assume then we wanted to optimize on those true positives. Now, the next question then is, where do we set this threshold? Is it 50%? Is it 10%? Is it 90% or whatever? And that's what this ROC, this receiver operating curve, helps us to do. And in fact, if we go back to the Python code, I'm actually going to change the Python code a little bit. And I'm going to change this X label from false positive rate, because that's just the opposite of the true positive rate, to threshold. So that's really what this chart is showing us. If I run this again, so it's one of the nice things is you actually change the Python code directly in the cells. So what this is telling us then is if we set a threshold of 0, so that means that we designate everybody as non-diabetic. Yeah, then we're going to get a 0 true positive rate. Okay. On the other hand, as we increase this threshold up to say 80%, our true positive rate is up to about 95%. So we would have a conversation then with the doctor about, what is an appropriate level of misdiagnosing negative patients so that you get as many of the positive patients as you can. And it looks from this chart that kind of around this kind of area is kind of a good balance between getting most of the diabetic patients without misdiagnosing the non-diabetic patients.
So let's say we, for the threshold that we had for 0.5, that's an easy balance. But let's say we move the threshold to like 0.8.
Yeah.
That means we'll have more false positives.
It will capture more of the true positives, and fewer false negatives,
fewer false negatives, because now you put the threshold high, so it'll be harder to predict whether somebody is diabetic, and if we do, they'll have a higher probability.
Another thing this ROC curve does is it tells us something about the sensitivity of choosing that threshold as well. And another metric, going back to this discussion about metrics, is the area under this curve is kind of a measure of the overall accuracy of that model across a broad range of different thresholds. And we can sort of calculate the area under that curve and use that as a metric, as we can see in this next section here. There's actually a function in Scikit-Learn called ROC AUC score. AUC stands for area under the curve. And so if I run that particular code, it tells us 85.6%. So that's another metric we might want to use if we're concerned about the effect of thresholds on making these diagnoses or predictions. All right. So we're going to do a little bit of a change of gears now and start talking about pipelines. And this is your area of expertise, Ruth. So tell us a little bit about pipelines and why we would want to create one when we're fitting models like this.
So pipelines are basically what it sounds like. If you want to do a certain number of tasks, you be like, okay, first I want to do this, then I want to do that, then I want to do. So it's almost like you're making a list of hierarchy lists as you're running, let's say for your training model. As you're running through, you wanted to do this first before it gets to the next stage. So in our use case, if you can scroll up a little bit. Okay. So remember initially when we started off, we had to specify what our features were and what our label was. In machine learning, we want to specify what columns are actually numeric, because the more numbers we have, the faster, the better performance that your model is going to run. And one of the things for numeric, the thing that we're looking for is making sure when you have values, let's say you mentioned like the glucose levels, right? We're seeing a lot of 80s, we're seeing hundreds and whatnot. Let's say we're dealing with another use case and we saw 1,000. You have like a mean of data, then there's an outlier that can skew your prediction. And, your accuracy, your performance may not be as good. So that's why for like numeric values, we want to specify which columns are numeric and use the scalar function to scale everything down into like a more what's it called, comparable
So like maybe if I
level.
had one variable that was between like 0 and 0.01, and I have another variable that's between minus a million and a million, we're going to squash them all down to be kind of the same kind of range.
Yeah. So I hate to go off topic, but like when you have like a picture and you need to zoom it down to maybe to fit a page, you're going to zoom it down. But does a picture, let's say is a picture of a cat, does it change into something else? No, you still have that picture of the cat, but it's just scaled down into a manageable size.
And that's what this standard scaler in Scikit-Learn does, right? It's just taking these numeric variables, scaling them to a common range.
Yeah. Then we also have, we call categorical for the ones that are like maybe strings. So if you have like text in the data set, then for that, we use something called, there are different, what's it called, transformations that you can use. But in our case, we're using one hot encoder. Sorry, I'm getting tongue-tied. But one hot encoder basically is taking all of your values. So if you have just normal text, it'll just put them all into, each text will have like a different unique number.
That's right, yeah. And because we're applying it in this case to the age variable, it's doing something quite interesting. What it's doing is essentially converting age into a categorical variable. So rather than saying things like, if your age increases by 5 years, then your probability of diabetes increases by 3%. What it's actually doing is dividing up the population into everybody who's 18, everybody who's 19, everybody who's 20, all the different ages that we have, and basically saying that at each age level, there is a completely potentially different propensity to diabetes. So it's a way of handling the fact that diabetes might relate to age in an unusual way, and we'll see how that affects the accuracy of our model in just a minute.
Yeah. So once we specify what the fields are, the transformer actually is the one that is actually going and doing the transformation. So scaling it down or putting it into those boxes that Dave mentioned for each age or each value, string value. Then the next thing is a pipeline. So the good thing of a pipeline is you put it into steps. You say, okay, before you run this model, the very first thing is go through and do the pre-processing. So what is in the pre-processing? Make sure you scale my data into a reasonable range. Once you do that, then the next thing is you can call the algorithm for running the classification. So in our case, we're using the logistic regression. So it's just calling that. So everything is comma separated. If you had other things that you wanted to do in between, you just put those.
All right, so we can define like a sequence of steps of, transforming the data, doing other kinds of aggregations, and then ultimately fitting a model, and then kind of run all those steps at once.
Exactly.
Yeah, and that's what the pipeline.fit function does here. So we can go ahead and run this block of code, and it's going to go through all those steps of defining the pipeline, and then actually run the pipeline in the next.
If you can go back, Dave.
Yep.
So if you notice, we did a print, and it shows a blueprint of that pipeline.
Gotcha.
That just means when you run this in, let's say we decide to take this model in production, right?
Yeah. Gotcha. That didn't actually run anything. That just defined the steps.
Yeah, it's just defining the steps. So when you bring in new data, it goes ahead and does the same steps before it does your prediction.
Okay. So that looks like that's what's happening here, right? So we got a new set of data with the X-test data. We're going to run through the same code that we did before.
Mhm.
and calculate all the same statistics that we did before. We've got all the accuracy statistics, the confusion matrix, we've got the RSC curve. So pre-processing the data has made a difference, because remember, our accuracy score was down at 78.9 before, I think, and now that we're treating the age variable differently, we've got a model with a much higher AUC, higher precision and accuracy as well. So that's kind of interesting.
Yeah.
But what if we wanted to do something different? What if we wanted to do, say, random forest instead of logistic regression, or just try a different kind of algorithm as well? Maybe that's going to give us better accuracy than playing around with the parameters or the pre-processing in a logistic model.
Yeah, actually, that's part of the things that I remember when I was first learning machine learning. I thought there was just, okay, give me one algorithm and call it a day. I just know that one classifier algorithm. But the good thing is, when you hear of multiple algorithms, that just means, like, within, let's say, classification. The difference is they're different algorithms, and each behave differently. So since we're talking about tuning, first we use regular logistic regression. Then the next thing we did was, okay, let's try and scale the data so it can improve our model. Another way that we can improve this classification of diabetic or non-diabetic is also explore other algorithms. So we have the supported vector machine algorithm to consider. We also have tree-based algorithms out there. Then we also have something called ensemble algorithms. And ensemble is just multiple different algorithms.
That's absolutely right. Yeah.
Yeah.
And this actually relates to a question that came in from Kevin on YouTube, I think. Kevin asked, like, what are the procedures to validate the model trained and its accuracy? Any important things to pay attention to? And this is one particular thing to pay attention to, is that different types of models might work better in different kinds of situations. So it's definitely worthwhile trying different types of model types depending on your particular application. And that's one of the really nice benefits of setting up everything in a pipeline, is because we've already standardized the process of reading in and preparing our data. If we want to try a random forest classifier instead of logistic regression, we can just use that pipeline we've already created. And all we need to do is change it from logistic regression there to random classifier there. And then, Kevin, to your question, we can use all those same statistics that we were looking at earlier on, the overall accuracy, the precision, the recall, against our held out test set to evaluate not just the logistic regression model, but compare it to a random forest classifier or a tree-based model or a support vector machine, all the different kinds of techniques that we might want to try. All right, so let's actually have a look at the performance metrics from our new model now that we've defined the new pipeline. So this is exactly the same set of codes that we just ran, but we're just using the newly defined pipeline that's using the random forest. And, well, this is really obvious when we look at the RSC curve. You know, it's really bent up into the left. It's got a very high area under the curve, 98.2. And the random forest model is doing much better than our logistic regression model when it comes to overall accuracy for this diabetes data. And that's pretty common, actually. Random forest models are super powerful. They can very easily pick up unusual non-linearities in your data that generalizes well to data that the model hasn't seen, as we can validate from looking at this in our test set. So that's a really good lesson there. So thank you for that question, Kevin. All right, and just to wrap things up, because we're just about out of time here, once we have done that, we can use our model for inferencing. We can just save the model that we want to use out to a pickle file with this joblib.dump function. And then when we're ready to actually, say, embed it into a clinical application, we can load that pickle file back in and then use that to generate predictions from a brand new data point that we've never seen before. So a new patient walks into the doctor's office, we measure their blood glucose, we measure their weight, we measure all 5 other variables, and then based on our random forest model, it's predicting that that particular patient is indeed a diabetic patient that deserves follow-up.
I feel like this deserves an applause.
Exactly. Well, actually, I think what it deserves, Ruth, is a knowledge check. So why don't we do a little test? Let me test your knowledge on some of the things we've learned here today. And by the way, everybody that's listening at home, you can play along too in our poll. Just visit akka.ms/polls or scan the QR code on your screen and you can participate in the poll. And Lauren will tell us how many people voted for which one, I believe. So let's have a look at the first question. People at home, go ahead and vote. So Ruth, you plan to use Scikit-Learn to train a model that predicts credit default risks. So a different application this time. And this model is going to predict 0 for loan applicants. That should be automatically approved.
Okay.
But it's going to predict a 1 for applications where there's a risk of default. And in that case, you would probably have some human consideration before making that model. So what kind of model is required? Is this A, a binary classification model, B, a multi-class classification model, or C, a linear regression model?
I know we didn't cover multi-class, but one of the telltale signs is the fact that we're choosing between 2. So 1, the hint I'm getting is if it's 0, we're approving the loan. If it's 1, we're not approving the loan. So since we're choosing between 2, I'm assuming it's a binary classification.
You are absolutely correct. That is indeed a binary classification model. And we can see that everybody online voted for that as well. So I'm glad everybody picked up on that, that when you're predicting a limited number of classes, that's a classification model, in this case 2. So it's a binary classification. When you're trying to predict a number that can be anything in a range, then that's a regression model, which is not the case for us in this case. So next question. You have trained the classification model using the Scikit-Learn logistic regression class, and you want to use that model to return labels for new data in the array x_new. Which code should you use? Is it A, model.predict on x_new? Is it B, model.fit on x_new? Or is it C, model.score on x_new and y_new?
Well, I like to think through the answer. The fact that we've been using model fit whenever we're training, that's training. So I'm going to go with model.predict since it's brand new data that we're looking at.
You're absolutely correct. Model.predict it is. Model.fit, of course, is for training the model, not making predictions. Scoring is a word that's often used synonymously with predictions, but that's not the case in this particular one. And I can see that 100% of our audience got that one right as well. So well done, audience.
Wow. Our audience was really paying attention.
All right. And last knowledge check. Ruth, you train a binary classification model using Scikit-Learn. And when you evaluate it with test data, you determine that the model achieves an overall recall metric of 0.81. What does this metric indicate? Is it A, the model correctly predicted 81% of the test cases, or B, 81% of the cases predicted as positive by the model were actually positive, or C, the model correctly identified 81% of positive cases as positive?
Yikes. We're not judging here, right? Because I have to choose between 2. So Is it B?
It is C. It is a really confusing one. I always have to stop and think about recall versus precision. But the way that I remember it is recall is about the data and precision is about the model. So in this case, recall is about identifying the positive cases in the data correctly as positive. So that makes it C.
Yeah,
And
getting that.
yeah, our audience was also a bit confused on that one as well. But don't feel bad because I've been doing this for 20 odd years and I still have to stop and think about that one myself.
Okay, this is judgment-free zone.
Okay. Well, I think that's just about all the time we got for. We got time for maybe just a couple more questions online if folks want to drop another one into the chat. Just to wrap up, I hope that during today's session that you've learned how to use when to use classification and how to evaluate and train classification models during Scikit-Learn. And if you haven't just yet, you can go back and run that Learn module as many times as you like. Practice it in the online Jupyter Notebook. Play around with the code. Try different things out and see how it works. It's a great environment for learning about classification models. And if you want a bit more of a challenge, if you think you've learned what it's all about, we prepared a whole new data set for you about wine. You've looked at this data set. Ruth, tell us a little bit about it.
So I love this. After taking this module, I wanted to apply it to real life situation. So it's actually looking at the different grape types. So you look at the grape types and you be able to classify the type of wine it is. So it is kind of fun. I like this one.
All right, great. So and if you want to try that out, you can find that on Unit 9 of the Learn module you've already been looking at. There are links there, or you can follow the link or the QR code right on this screen here. But I believe that is all we have time for right now. But do go ahead and try out the classification module. Here, I'll drop in this link to the current Learn module in case people have missed it. I do see we have one more question that's come in again from Kevin. Thank you, Kevin. Kevin is asking, can I know which types of cross-validation should we use correctly? So what kind of cross-validation should we use?
That's usually, it all depends, right? It depends on how granular you want to dissect your data and analyze the different subgroups when you're doing the testing. And actually, it's actually good. The higher, the better. But yeah, it exposes different cohorts of your data that your model may be performing poorly in.
Yeah.
So yeah, I'll say it's something that you play around with. Rule of thumb, I think by default, people usually pick 2, just slice it in half. But yeah, I think I've played up to 4. But yeah, it's actually a good way to also measure performance.
Yeah, and there's one other thing that Kevin might be referring to there. There is a technique also known as cross-validation, where essentially we can resample from our original data sets and use that to evaluate the performance of our model. It's a bit beyond the scope of this particular sort of level here, but if that's something you're interested in, Kevin, feel free to reach out, and I'm happy to point you to some resources about cross-validation there as well. Laurent, do we have any other questions coming on the queue? I'm hearing from Laurent that there are no more questions, but thanks everybody for your attention today. And Ruth, why don't you wrap us up and tell everybody about the next Learn Live session?
So we have another exciting Learn Live session. It's called learning how to implement compliance for Microsoft Teams. So this is going on October 24th between 1 and 2:30 Pacific. And if you want to prep ahead of time, these are the hyperlinks to learn a little more information about the course. But it's another exciting course to take, especially now that Microsoft Teams has a lot of brilliant, exciting features. That reminds me of all the announcements we made at Ignite. I'm like, I can't wait to go back to watch Teams.
Yeah. And the other thing I'll mention to folks is there is a great archive of recorded Learn Live sessions on dozens, maybe even hundreds by now, different topics of people running through Learn modules in Microsoft Learn. Have a look at that link on the top right-hand side of your screen, aka.ms/learnlive, to check out the archive, and lots of recorded material there as well. But thank you so much, Ruth, for coming along today and being our partner. And thank you, everybody, for joining. Bye-bye, everybody.
Thanks, Dave. This was fun.
Thanks, Ruth. Bye-bye.